Hi, I'm Sarah. I'm a programmer. Beep, boop, beep. Take my bills very, very seriously. I have a QR code here. If you scan it, you can follow along the slides on your own device. You don't have to, but some of the links will be easy to click to go to any kind of reference. Pause it. I put everything together today. I am a self-taught programmer. I'm a full-stack senior software engineer currently working in a bioinformatics engineering team. I have a passion for where math meets programming. I'm heavy in .NET. I've filled startup CTO shoes, and I help run Hack Augusta. I have hedgehog stickers for anyone that likes this guy here. This is a Sustainable IT Manifesto mascot. Myself and my co-chair Kelly are here speaking, actually both of us speaking. He's speaking tomorrow, and we have plenty of hedgehog stickers if anyone wants them. Oh, let's see, yeah. So if you are on your device, you can click any QR code or any link, but these two will be my LinkedIn and my GitHub. And on that note, I'm gonna be that person. I didn't listen to every single speech today, but if no one else has said it, I'm going to. I encourage everyone to get their phone out right now, go to LinkedIn. If you don't know how to use the QR code feature there, I can tell you, but connect with somebody you don't know around you. You're gonna leave, you're not gonna, like, especially in a single track conference, you get the chance to talk to people about the same content. Don't miss that opportunity. There's gonna be a lot of people at this conference that you will see every year, and it's special. So, does everyone know everyone around them? No? I see no one moving. There's some smiles. All right, yeah, so Hack Augusta is similar to some of the the meetup groups in this area. I bring it up because it's something that I connected with Barry on. I connected with multiple people last year about it. There's a lot, especially outside of Atlanta, that the Southeast kind of missed from COVID tanking things with tech meetups and community. Speakers being one of them, and I've tried to work with people and support people where we can. Hack Augusta is still kind of regrowing, but the mission statement that they've had for a long time, much longer than I've been there, stands up to me, so I like to read it. But Hack Augusta. We believe the world is a better place when every community supports its creative class of hackers, artists, makers, and entrepreneurs. Hackers, artists, makers, and entrepreneurs. We are the creative class that makes cities worth living in. STEM. To me, this is STEM. And it's important to me for every single tech talk I ever listen to, whether it's 5 minutes, hour and a half, an entire workshop. It's important to go into it in context that lets you absorb what you're there for. Whether that be the community, the content, the growth from a specific niche, doesn't matter what it is. You need to be able to absorb what you're there for. And you have to be in the right mindset to do that. So I like starting my talks with the intro to Neil deGrasse Tyson's Starry Messenger. I know that it is available freely on his website because it's the intro, so I know I'm not infringing on any copyright when I read it. But it's important to me to set the stage, and I hope it makes a difference to all of you because I think it is an important message, especially coming from an engineer. But it is. Starry Messenger is a wake-up call to civilization. People no longer know who or what to trust. We sow hatred of others, fueled by what we think is true, or what we want to be true, without regard to what is true. Cultural and political factions battle for the souls of communities and of nations. We've lost all sight of what distinguishes facts from opinions. We lob grenades at one another when we could be sharing beers in pubs. When Galileo Galilei published Sidereus Nuncius in 1610, he brought to earth cosmic truths that had been waiting since antiquity to descend upon human thought. Galileo's freshly perfected telescope revealed a universe unlike anything people presumed to be true, unlike anything people wanted to be true, unlike anything people dared say was true. Sidereus Nuncius contained his observations of the sun, moon, and stars, as well as the planets and the Milky Way. 2 fast takeaways from his book. 1, human eyes alone are insufficient to reveal the fundamental truths of nature. 2, Earth is not the center of all motion. It orbits the sun as just one among the unknown planets. Sidereus Nuncius translates from Latin to starry messenger. These first ever cosmic perspectives in our world were ego checks on our own self-importance, messages from the stars forcing people to rethink our relationship to one another, to Earth, and to the cosmos. We otherwise risk believing the world revolves around us and our opinions. As an antidote, Starry Messenger offers ways to allocate our emotional and intellectual energies that reconcile with the biology, chemistry, and physics of the known universe. Starry Messenger recasts some of the most discussed and debated topics of our times: war, politics, religion, truth, beauty, gender, race, each an artificial battlefield on the landscape of life, and returns them to the reader in ways that foster accountability and wisdom in the service of civilization. I also intermittently explore how we might appear to space aliens who arrive on Earth with no preconceived notions of who or what we are, or how we should be. They serve as impartial observers to our mysterious ways as they highlight inconsistencies, hypocrisies, and occasional idiocies of our lives. Think of Starry Messenger as a trove of insights informed by the universe and brought to you by the methods and tools of science. To me, this is STEM. STEM, science, technology, engineering, math. It both reflects on the past and propels us forward. Combinations of the components of STEM build the communities and realities that we live in. A common quote of mine is something like, in many ways, software runs this world. And I rate that every day. I'd like it to matter. So, we come to places like this, right? We come to do this, and especially at such a polyglot conference, you have those components, and we all have those pieces that mix together, and it's really, really awesome. So, as a transition into the math, who here is a programmer? Do you consider yourself part of STEM? Yeah, right. It seems to be a harder sell for some people. It's really interesting. There's an E in there that's engineering, and it's in software engineering. But the M is math, and that's what I'm going to get into today. As the outro. If you're here today, you are a part of STEM. You're part of the creative class that makes cities worth living in. The name Hack Augusta comes from the concept of hacking the community to create a culture of innovation and collaboration. This is STEM. So yes, let's discuss the M in STEM, math. Many programmers claim they don't know math. At least one of them did today. But if you just thought to yourself, yeah, that's me, today I'm going to try to convince you that you know more math than you think. And if you think you know math, let's see if I open your eyes to anything today, or if something catches your eye, and feel free to comment about it directly to me. Or I don't think I created a channel in the Zulip yet, but feel free to. I also, at any point in time, always accept math jokes, just on a regular basis. So feel free to flood them in there. Let's see. Yeah, number sense. What is number sense? I think I have a strong number sense. It's the intuitive understanding of numbers and their relationships. It begins with understanding concepts like quantities, more and less, bigger and smaller. To understand these concepts is to understand mathematical logic. Mathematical logic is comparable to programmatic logic. Engineers intuitively grasp mathematical concepts every day. Number sense is the ability to recognize patterns, estimate values, manipulate numbers. It is foundational to logic and programming. Something that I wanted to answer for this talk, and I didn't quite get to it, is what makes concepts tangible? Why does that matter for engineering and number sense? What gives you that tangible grasp of quantities, bigger and smaller? That'll be maybe it'll be next year. But let's see. Who knows what this is? I know some people do. Yeah. How many of you understand it? I know people do. Yeah. Yay. So it's sigma notation. You complete the operation to the right, starting at the number defined at the bottom and going to the number defined at the top. You do this for each increment, adding to an overall sum. Who knows what this is? I get varied answers. I'm like, Usually people try to guess the language. That's not what I was going for. It's a for loop. Oops, sorry. And they're the same thing. Oh yeah, right. I edited this for a group that was math heavy, and when I made it, I put it into JavaScript, and I laughed at myself thinking, I don't know how many equals to give it, so I just gave it 3.14 because pi works into this. I made the if you want to argue about the ability of that, you can reach out after, we can work out some numbers. We'll figure it out. But this enemy is the same thing, so we have for loop. Let's see. Yeah, so you're starting at 1, ending term of 4. They're the same, the operation. So does this make more sense to anyone now that didn't before? How about if I do that? Same concept, or does it seem, I saw a frown back there. How about that one? I only added it in because while I was reading this talk for the first time, this actually came out. So if you are following along, you can click on that little pie because it's a link. But if not, I can add it into the chat later. But this actually came out while I was reading the talk, so I added it in. I don't actually want everybody to try it. I mean, you can, feel free, but it's not required. You can go for this one. All right, that makes sense. Let's see. Oh, yeah. All right, so how many of you at the beginning of that felt like you didn't understand what that first bit was? And then now, does it make more sense? He's like, maybe. Keep going, we'll tell you later. Feedback at the end of the day. Let's see. Yeah, good number sense is foundational problem solving. How many of you would call programming problem solving? Right, okay, you're more on my, yeah, I've had not as many positives on that, and I mean, right? It's literally what I do for a living, I don't think. But yeah, it's astounding how it can relate to everything. So math teaches logical reasoning and problem solving skills that are essential in programming. It helps break down complex problems into smaller, manageable parts, similar to how you might approach rating a program or debugging code. To quote a friend who spoke last year on Perl, my high school geometry class is what helped me to start excel at programming. My teacher taught heavily proof-based geometry, and it really helped me figure out how to break big problems down into smaller ones. It's foundational to everything we do. I mean, it's engineering on every level, and it's number sense. Math is logic. Programming is logic. But this talk is trying to focus on numbers specifically. So we're gonna venture, from another quote in here from different ones. I squished everything together when I was trying to fill the hour. But yeah, let's adventure beyond bits and bytes and talk about the numeric foundation of programming. Precision versus accuracy. If precision and accuracy sound familiar, you've probably taken a physics class. Probably. Does anybody feel traumatic from it? Like, no? Good, that's great. All jokes aside, in the world of programming, there are distinctly different concepts. Sometimes with profound impacts. Precision is like fine details. It's the level of detail or exactness in a measurement or calculation. As an example in programming, this translates to the number of decimal places a calculation can represent. Accuracy is like closeness to the true value. It's about how close a result in measurement or calculation. It's not about the number of decimal places, but about the correctness of the outcome. Closeness to the truth. Precision is about detail. Accuracy is about correctness. Context determines the right approach. And language, really. But like, what does that mean for us? It kind of depends on what you're working on and why. But most languages, most jobs, most reasons, you are not going to need that accuracy. And it's going to be at the cost of efficiency, memory, speed, all kinds of things like that. So if you are not doing maybe money, is what I have it in here. Financial calculations, scientific measurements. It's a big difference, and knowing your language is powerful too, because, let's see, do I have a C# one in here? I chose C# because I know the double and decimal is a really clear example. That is, yeah. Got worried I had the JavaScript in there for a second. This one's just dealing with pi as the example of the decimal points, but this is C# representing a decimal and a double, where you have, see all the zeros and the 4? It's not accurate, but it's fast, so it depends on what you're doing. The binary result, which is the double, is faster, but it has a small error. The decimal result is slower, gives you the right answer. That's because binary is base 2. It's most efficient for computer processing. You don't have to translate anything. They know what it is already. But small errors can accumulate, kind of like how banks have been found to be doing that and end up with a very large amount of money from these very tiny bits that they were doing wrong. Decimal does need to be translated. It's base 10. It's precise calculations, but it's slow for computer processing. It requires a conversion. And then, so you're typically going to be using binary. A reason to know that is because you choose the types, well, depending on the language, you choose what you write in code, so understanding the difference can matter. Here's that one. Yeah. Math is deeply embedded in programming. Understanding number sense, precision versus accuracy, binary versus decimal, it helps programmers write more efficient and effective code. So next time you think, I don't know math, which doesn't seem like a lot of people here, you use it every day, so you can recognize it in yourself more. Yeah, random numbers. Oh yeah, that is 3, 1, 4, 1, 5. I believe it is depicting fractals of some sort, but I was not the creator, so I didn't quite get the reference with pi and it. Anybody know why I'm talking about random numbers? Has it been done at like a lot of places that everyone's gone? I like it. I think it's a fascinating concept. It relates to cybersecurity a lot, so I thought it was the most appropriate for this conference, but I only have a little bit about it. But generating random numbers is difficult because true randomness is rare in computers, which are deterministic systems. I'm not talking at all on the quantum side on this talk, but algorithms typically generate pseudo-random numbers. I have, I think, example of math.random for JavaScript, but most languages will have, whether it's in a math library or not, an ability to generate a pseudo-random number. That is sufficient for everyday uses, not sufficient for cryptography, which is why Cloudflare uses natural. Let's see, I'm completely not paying attention to what I actually wrote, and I'm going off. Let's see. Yeah, algorithms typically generate pseudo-random numbers based on an initial value of seed. While these can appear random, they can be predictable if the seed is known. Achieving true randomness requires unpredictable inputs like physical phenomena which provide higher entropy, like nature, making them hard to predict and ideal for secure applications like cryptography. Cloudflare does this with lava lamps. They use a wall of lava lamps to generate random data for encryption. Photos of the unpredictable movement of the lava provide entropy, which helps create secure I'm going to skip that word. For encryption keys. This process ensures strong randomness, which is essential to preventing and predicting encryption. I think one of these is clickable, but if anybody doesn't know anybody and wants to look it up, you can just search Cloud for lava lamps. It will come up. There's lots of information about it. Oh, there you go. That's the link if anyone is following along. But pi. Let's see. This one had to do, it was like 2 years ago on Pi Day. I try to do something new with it every year, especially when we have new options coming out where I used JavaScript that year and you could get a string of pi in digits that was 1 million characters long. So you can just import that and really play with the numbers, especially in JavaScript, because never mind. So on this one, I don't have a lot fledged out with like the law of large numbers and having randomness get to even amounts, but I'll show you what I mean. So I grab pi to 1 million digits. I'm using this library, so then I have pi string. So starting to the right decimal point. So I loop through 10,000, 100,000, 1 million, 10 million, and 100 million times, and I compare that to JavaScript's math.random. So on the top here, I'm getting a random index of the pi string. I do that differently in the future. And then down here, just a random one. So comparing pi and math.random in the 1,000 loop is the most obvious because you're not reaching times where, in those big numbers, it's easier to hit those like even amounts. I don't think I'm explaining this well. But in the 1,000 loop, each one of these individual digits appeared this many times. It's almost exactly even in pi, versus doing math.random gave me this numbers. These are actually closer. I think it's fascinating. It shouldn't be that easy, but 10,000 loop was the same, 100,000 loop, 1 million loop, 10 million loop, 100 million loop. I broke it down into percentages, and again, you see the differences in the smaller numbers. So 1,000 being the smallest. You're still almost at 10% for every single one, and that's by grabbing a random index of the pi string, so a random digit from pi versus math.random. And then this one was looping through in order, but I did do a million, I think. Yeah, so that one I want to go back to because there's a few pieces of the numbers that's really interesting to see what the numbers are doing, but even grabbing smaller amounts of them, you're still getting almost even distribution, and I think it's fascinating. Oh, right. I keep surprising myself because I don't remember what's in here. Number sense. This one has to do with an Euler problem. Who's done those? As long as it's like advent code and leet code, except Euler had a lot more math going on, right? This one stood out to me because when I first solved it, I completed it quickly, but it was a 10 to 15 minute run on a modern machine. So it was not a fast algorithm. And I took a look at my code. So it's setting you up to have sequences of numbers. So you're looking at terms, and it's triangle numbers. So 1 plus 2, here I have there. So you want to list the factors of the 7 triangle numbers, adding each time. So from 3 you get 6 for the next triangle number, 10 from that one, 15 from that one, 21 from that one, and 28 from that one. So 28 is the first triangle number to have over 5 divisors. It's asking you which is the first to have over 500. So you have to loop through a lot, and looping is one of the most costly things that you can do in algorithms in any data set. Looping is going to cost you. So the biggest thing to understand with that is how to reduce your search area accurately. On this one, I thought about what divisor pairs meant. So if I'm in the beginning and I know that for triangle number 78, I have 1 and 78, 2 and 39, 3 and 26, and 6 and 13. So if I'm starting in the beginning and I'm looping, I'm going this way, what happens here? I know that if this isn't the answer, or if it is, there's never going to be anything larger than it ever again. That's not how it works. So when I get to 2, and I know that this matches, no numbers will ever be above 39, ever. I can cut that entire search area out. I don't have to look at it. Now this took me 4 steps to get to, I don't have to check again. But imagine when you reach those massive numbers, like I don't think I have the printout here of what the number was. It's a very big number to reach 500 divisors. But I'm cutting the search area in half every iteration. I went from a 10 to 15 minute algorithm on a good machine to 300 milliseconds. I wish I could do that for production sometime, but I'll hold on to this one until then. It was just a tremendous difference. I'm sure a lot of it too is luck with numbers, where what kind of divisors, if it's an even number is going to be a big difference because you're going to have 2. You can always cut the search area in half when it's even, which is where I went first, but this got me a lot farther. This one has so this link here goes to that problem if you're interested in looking around yourself. I can provide, this is a static GitHub page, so I can provide this link in the chat after, so everyone can, yeah, I guess that's the end. Oh wait, but you get a slice of pie at the end, and this one, right? So that way, I don't have the code on this one. I'll put it up. So I wrote, I think it was another Pi day. I had so much fun with this. I think it was in the process of doing a lot of like the Eulers and stuff. I was doing a lot of in JavaScript. And I do a lot of logging in JavaScript when I'm debugging, and the plain white and black just doesn't help my brain. I like colors, so I wrote a library for it because I like rainbow. So this is a library that you can get on, it's not in NPM, but it is on GitHub. And I will provide the link for that because I didn't add the QR code. But it does just ENC colors for console printout, as well as rainbow foreground and rainbow background. And that's how I got pi. I'm like, I can't be anywhere near an hour. Yeah, nope. But I have lots of things I could add to it. We can bring up that library. I went a lot faster than I thought I would. Does anyone have any questions? We can go back into, oh, I don't have the code on here. So we can go back into the random ones.
I have a question. So you cut down your data space with each go. Mm-hmm. Did you consider doing any memoization?
Not on that one. Because it was, my first notion was, well, not every number is going to be an even number, but I would normally look at cutting that area in half if it is an even number, but it's only going to be half of them at best. That's how I ended up with cutting the search area down with the other side of the factor pair, but it was very fast and easy with like no code changes, and I didn't go anywhere after that. Would you like to expand on that? Like, what would you have looked at?
I might have, you had already solved 13 or what have you, so you wouldn't necessarily have to.
Yeah, because let me bring it up.
He's saying that you solved the problem with dynamic programming, right?
Wait, was it this?
You solved it with dynamic programming?
And he's talking about
memoization is if you've already calculated something, store the result, so you don't have to calculate it again.
Dynamic programming.
So I'm trying to think of, because realistically, you're not really saving this because you're checking for number of divisors each time. So it would be computational for each number, yeah, but then not again after, yeah. I was trying to remember the 13, yeah, like here. Of divisor pairs for triangle number 78, because you have to compute the triangle number first, but that's fast and easy. That's the code for this here. I wasn't looking at it. Checking for divisors, because I can add that in actually on any of the layers. Oh look, there's your triple equals. Is it more just like what I look for in problems that I'm tackling? Gosh, I think anything that I hear about, get interested in, I've tackled a lot. Actually, thinking about for loops in Sigma was from discussing Euler problems with another programmer that has been doing it a whole lot longer than me, and we had a discussion about how Euler in particular, I think, is an example of, it's not really about the programming, it's that you gotta know the trick. Like knowing search, like binary search, knowing an algorithm, knowing that something exists, and if you don't, you may not be going down a path that's going to take you anywhere at all. And we kind of argued about it, and he had an example of, he didn't think he knew math, more or less. So he goes like all the way to the end of one of like high level Euler problems and was looking at it and like, see, look, I have no idea what this is. And I'm like, oh, that's a for loop. I can show you. And it just blew his mind. And he started doing much higher level Euler problems, like he had never considered before, just because no one had pointed that out to him about the steps being the same. So it's fascinating. I mean, realistically, it can be comparable to programmatic syntax with math in different languages, where if you don't have a library that's covering something, or you're coding something from scratch as opposed to using an existing extension method or an algorithm that exists, whether it's in the language that you have or not, like math.random exists for JavaScript. There's massive tool differences with math in different languages. I have not toyed with math in all languages whatsoever, so I probably don't have the best comparison for them, but I can probably, I'm not sure what direction you were going with in the sense of being interested more. Yeah, like Eulers. I think a lot of that comes from, especially in this day and age, so many of us are just so remote. We're not in the same places. Why co-working spaces now are becoming more popular. We're not around other people that are solving problems. We're not hearing somebody go, oh, I can't reduce this search area, I don't know. Or like, hey, have you ever done an Euler problem? Like, or heard it pronounced Euler? Instead of, just, Everybody's SQL, SQL, whatever, you know, people don't hear things differently. So it's kind of the part of the point with this is any kind of engineer knows more math than they think. Like even people that think they do, you know more. And yeah, you really should be leaning into it. I mean, a lot of it is about number sense, and if we had more teams or people in general feeling comfortable with those conversations, imagine where we'd go. And it's a funny joke about, haha, math nerd, you know, I know, I've heard it, I get it. Like, but if you lean into it, the kind of growth and side quests, and I mean, that's probably why half algorithms were ever written. I mean, if you read like the history of algorithm creation, a lot of them were, oh, I wanted to solve this thing a different way, or I had no idea something else existed, so I started a different thing from scratch for absolutely no reason, and I found this amazing, right? That's how it works. On that note, like, I have them over here. I brought 3 books with me that are really interesting one's about math, and then I think 2 of them are more about algorithms, but I was hoping to open them up and have like inspiration. I didn't quite get there, but it sounds like you would like looking at all 3 of them, and I will bring them out here afterward. I can send a picture in like the chat. Yeah, I hear what you're saying. Like, have you done Euler's? Start with that. You know, it's an honor system, but Euler in particular is one where a lot of people will have published what they did, which can be very helpful after you've solved it, or maybe you feel like you didn't go in the right direction, you know, do it however you want, but people that maybe have a propensity for that, or maybe they have training in like your different silos, which is really where things come from, like growth. I like hearing what other people have done for it, so I like to look that up after I've solved them, or if I get really stuck, because it's not like a life or death situation, I'm not getting to the end, I can look it up, it's okay, and then understanding it afterwards. So it's really nice that people have content out there, especially from COVID times on, because we've had a lot of people home with less to do, so we have a lot better content than we used to.
So what's your next math invention?
Oh God. I feel like the answer that my brain comes up with fastest is, so I'm in a newer position now. I'm working with lots of different kinds of data and values and types, and coming from different sources than I've done before. And I don't really know what I'm doing yet with all of it, but I like the idea that I get to find out. And through the process, I forgot I was gonna put in here the joke about like what the threshold is to call something big data. I remember the table that I was looking at that I was working with, I just happened to note in a meeting that I saw it looked like the results were coming back for 8.8 million euros, and I was just noting it and was told, nope, that's absolutely way too low. We should be doing something different. So it's good to mention the number sense like that. It's actually another note on, I guess it would be resources, memory, kind of depends on the specifications and needs. So I'm going to be pulling in data that the first run of it is going to be the heaviest, but it really does not need to be fast at all. It doesn't need, it can be batched, it doesn't matter, but they're still wanting me to present numbers on maybe doing like loops of 1,000 just to see like what the best option is, which I just find fascinating because speed doesn't matter and memory doesn't matter, so I'm not quite sure why we were going in that direction. But it can be really interesting to know, and I guess that leads into Nirvana's point about documentation, where something that I'm working with now is Snowflake, and I'm pulling from it with a .NET connector to bring it into a .NET app. And there's documentation on both sides on how I might be able to do like asynchronicity or different options on both sides. And understanding that is a thing, there is separation, like you might be making choices on both sides that actually counteract each other. Documentation, right? Like, I don't know where Ron is, I was gonna pick on him. He's hiding. But it's a big difference. Yeah, sorry, now I'm thinking about work. Here, if I go to, mine is wait, this one right here. No, wait, that's pi. I'm like, I might have a few things that are like that. It started with just doing like console colors. And so there's a lot of these on like NPM. If you go like, this would be another example. This is not mine. But you just have to know, like, bring it in and then know your syntax. They don't always have the best documentation on that, but this would be an example. There's chalk, I think, is another one that does some really funky things, but mine, I liked the rainbows. Like I said, indication, last call. This one is an example of just the plain colors, but this one here, I wish I had oh, actually it would be in Pi. Let me bring this up. Nope. We'll go. This will be here. Yeah, so using this guy here. So that's the library. Is probably too small. Is that a little better? Apparently I don't have that choice. Getting random digits of pi. Having to do with, let's see, iterations. No, that was a different pi day. Pi string, nope. Bummer. I probably have too many, but it's probably in here. I can find it and put it in the Zulu. There is it's a good syntactic example, but it's fun to toy with, but it's more or less extension to string. So in JavaScript, and you can just do dot. I think it's RFG for rainbow foreground, and putting the string in the parentheses, and you get your rainbow. Like, that would be this guy. That guy. I'm surprised I went through like